All right, thanks everybody for joining today. We have a bit of a continuation of a topic that we started last week. Last week we heard about network monitoring via NetSAGE. This week we're going to hear a related effort from the team at ESnet, and it's built off of the startings of the NetSAGE project, but this one is termed Stardust. And we have Ed, Andy, and Sowmya here today, and they are going to go into a little bit of detail about this and then show a demo later on. So I will turn it over to Andy to get us started.
I think Ed's actually going to kick us off, so I'll let him go.
Oh, there we go. Sure. Ed is going to kick us off, and Andy will drive the slides.
Yeah, thanks, Jason. Yeah, so we've got, I think in terms of planned content, about 40 minutes. And so I'll kick off and talk a little bit about sort of motivations and overview. Andy will jump pretty quickly into a demo of some of the base capabilities we have, and Sowmya will talk about some of the design details, and then I'll pick up the tail end and cover some of the future-looking sort of activities we have going on. But to start off with, thank you everybody for coming today. As Jason mentioned, a lot of what we've been doing in the measurement front within ESnet in the last year has been sort of a continuation of some of the ideas that we fleshed out as part of the NetSAGE project. And so much of what we're describing as Stardust can be considered I guess the TLDR is it's sort of like we took the NetSAGE concept, generalized it, and sort of deployed it and operated it at scale. That's probably the one-liner I'd say of what we're doing here. So in terms of motivation, right, in measuring networks, if you could go to slide 3, Andy. Yeah, just to kind of review, right? So whether we're designing and operating a network or just about any kind of infrastructure, right? We need to measure the thing we're running and check the performance of it, right? And so I think this audience has a pretty good understanding of what that all means for networks, right? But the end result is, in order to do a good job of it, is there's a wide variety of data sources that we need to collect, whether it be interface counters, flow data, optical light levels, CPU usage, or latency and throughput of TCP flows through the network, or even application performance, right? So database query latency, that kind of thing, right? So there's all these measurements. I think that the idea of observability has become pretty common in our industry. And at times we all know we can measure all the things, right? And we often find ourselves asking, is the juice worth the squeeze, right? So the orange juice tastes pretty good, but how much work are you going to put into squeezing it? And is there, for us, as we think about that in all these opportunities, there are ways to reduce the amount of force it takes to do the squeezing, right? That's kind of, I guess, the poor analogy I would use to what we've been trying to do with Stardust. So next slide, Andy. So, I guess the way to frame this as well is for us is storytelling. And, with any of these measurement systems, we have a variety of different stories, and there's kind of a logical progression that we see, right? So often we start collecting data, maybe at an operational level, to know, is the network up? Are the router CPUs okay? Is everything, the adjacencies there? Can we forward traffic? And then, once we know that, typically in over time, it's like, okay, can we use the same data to understand how to plan for capacity? So, what are the circuit trends in terms of growth and whatnot? And then, these last two classes of stories we often tell are build from there, right? So it's the community engagement. We have a set of users that use our network, and we want to make sure they're using it effectively and that we can help them and facilitate that, right? And then ultimately, what we really want to do is say, what impact does our network make on the communities that we serve, and how are we awesome, or what do we do to improve, that kind of thing, right? And in the end, it comes down to who, what, where, and why. And those are the types of questions people care about. They don't care how many terabytes of data you're collecting, because if you're not turning it into a good narrative that is fact-based, it's not really going to make a huge impact, right? So for us, in order to do that, to answer those types of questions, we really need to focus on the metadata. And a lot of that started in terms of how to associate the metadata with measurements started in Stardust, and it's something we've continued to do and tailor in the ESnet context with Stardust. Next slide. And so there's a series of problems we want to tackle, I think, as we looked at the legacy systems we had in ESnet, right? One is spelling errors, but no. The other one is, the main one really for us is that every time we wanted to add a new data source, there was this scale problem where the amount of work we had to do was proportional to the number of data sources, right? So whether it be unique presentation layers or storage or ingest requirements, in order to add a new data source, it required a lot of effort, and that became prohibitive, right? At the same time, we had a lot of use cases where the need for this observability became it wasn't optional anymore, right? People needed to know this stuff, and they really wanted that juice, right? They didn't care what it cost to squeeze. They wanted that juice. They loved that stuff. So that's the modern era we live in, and I think that's just, it's going to get, that's not going to go away, right? So the third issue we had was that, our understanding of the types of metadata that we would need to answer those kind of questions was still evolving. Oftentimes some legacy systems, you'd have to a priori know the metadata and associate it, and it was kind of rigid, right? And so we needed a sort of a flexible way of associating metadata with our measurements. So we kind of set out to, basically figure out how to create a better environment for ourselves and for our users, right? And so in our minds, what that meant was giving non-developers the ability to create analyses and visuals without having to code, right? So that's sort of doing things declaratively with a portal, or almost like a wiki, right? We wanted to leverage open source data, open source components to minimize that code maintenance burden or the bespoke development and test cycles that often slow down innovation, right? When we can. Obviously, we still have to do custom code here and there. And we need to support that evolving metadata, right? So we know that's going to evolve as our domain understanding improves. And lastly, we wanted a platform that would allow us to provide a basis for sharing and collaborating within the community. So whether it be sharing in terms of like metadata, actual content, or whether it was design patterns or code components, however you might define sharing and collaborating, we wanted something that we could help and work with the community on. So next slide, please. And, in terms of why in 2021 did we decide to tackle this? I think that's an important one, right? So obviously, we're coming off the heels of the NetSAGE project, but at the same time, there's some other motivators for us personally in ESnet, right? So the first one was we had this legacy approach, and it had served us reasonably well for years, but it was starting to show some limits, right? In particular, every time we wanted to make certain types of changes to the way metadata is represented or to new data types, that required a code release in a deployment sort of scenario, right? So there was a high, sort of high latency, high labor effort to add new data, right? And so every source meant that would be true, right? And so when you couple that with the fact that we had a fairly small team at the time, it meant we didn't really have the cycles to kind of do all the things that we wished we could do, and so that meant our pace of innovation was limited, right? I think was the key there. So in addition to that, we of course lacked the declarative editing features in the UI, right? So we had like the My ESnet portal. We still have it today. It's got some great visual concepts in it. A lot of those are defined in software, right? Or require a developer to edit into a software release. And so that's a little bit in limiting when you're a network engineer who wants to create something in 5 minutes to test out an idea, right? So, and then the broader context was the stars were starting to align, right? So ESNet's been growing as part of ESnet 6, and so we now have a focused measurement team. So if you look to the right, that is the set of staff that are on my team and that I'm very fortunate to have working with me. And so we have a very capable deep bench now that are able to do the kind of measurement work that we've always wanted to do, right? And in addition to that, the broader technical space is blossomed, right? So there's all sorts of compelling technology, whether you're a fan of Elasticsearch, which we'll talk about in a minute, or OpenSearch, or Telegraph, or Influx, you name it. There's a billion components these days due to the Internet of Things that are out there that are just ready to be integrated and leveraged, right? And a subset of those, as we mentioned with the NSF NetSAGE product, that basically vetted a desired approach of ours, which was a particular combination of of components that we realized could operate not only for the NetSAGE use case, but also for a generalized network measurement environment use case at scale. And so Sowmya will talk about that later, of course. So, and then the kicker for us was really the proximate cause for what forced us to sort of take action was we had a legacy flow analysis system that was, many years old and wasn't going to keep up with the ESnet 6 for a variety of reasons. The least of which was that, we had a license we couldn't renew that was limited in terms of number of routers it would support. So, so basically we had a team that could do it. We had an idea of how to do it, and we know we couldn't avoid doing it any longer. Essentially, that's going into late 2020. That was the sort of the landscape, as it were. Next slide, Andy. So we decided to come up with Stardust, I won't go into that where the name Stardust came from. It might be from a particular sci-fi movie, but we needed a new approach. And what we ended up doing was basically saying, let's see if we can take the NetSAGE approach and generalize it and create sort of this flexible environment, multi-data source environment that allows users to create their own analyses and potentially down the road, we're not there yet, allow them to be able to integrate their own data sources if they have some new data sources, right? And so we sort of took a fairly pragmatic approach, I would say, that was sensitive to our strengths, right? So it clearly built on our past collaborations, so we have worked for years quite closely with the NetSAGE project, in particular with IU in general and the global NOC in a variety of different ways, right? And so our approach has been to basically integrate where we can and innovate where it makes sense. And so for us, what that really meant was, we don't want to be developing a low-level time series database. What we want to be doing is working on applying our domain knowledge and expertise and visualization to get data into an existing database and get it out and make meaningful insights from there, right? And so we basically formed an interdisciplinary team within ESnet to sort of, we have lots of wisdom within the organization, whether it be in the software team, the systems team, or network engineers, right? So we have over 20 years of industry experience and end-to-end experience, across many of us, right? And we've been through this measurement environment game through multiple generations. So we've seen what it takes to run these things at scale. And additionally, we've been doing quite a bit of open source collaboration through the years, right? So whether it be through the PerfSONAR side of the house or iPerf or you name it, right? We've been around, we know kind of how that game works. And so, Q3 of 2020 is when we kind of figured out we had to do something. And in Q4, we basically firmed up our requirements and created a design and did some evaluation of a partial scale solution where we compared the derivative NetSAGE to essentially commercial alternatives. And ultimately in Q1 is when we started to sort of deploy full scale. And then from there, it's basically been, we went from that, let's replace the legacy flow analysis system to, let's see if we can replace some of our other legacy analyses in storage systems. So for instance, in this year, there's been a lot of focus on SNMP and optical data, as well as creating some new visuals. And we'll show some of that here shortly. So I think what we'll do now is I'll hand over to Andy and he can talk a little bit about what Stardust is and kind of give you a quick, just direct feel of what it's like.
Yep, thanks, Ed. So as Ed said, we kind of did this evaluation last year, which led to this service we call Stardust. So in terms of like architecture and technology stack, kind of also as Ed alluded to, we applied kind of many of the concepts and in some case directly the code from the NetSAGE project. And so in particular, NetSAGE was focused on collecting flow, SNMP, and PerfSONAR data. Right out of the gate, we obviously cared about flow because of that legacy system we're talking about. And what NetSAGE was doing for that was using a tech stack based off of Logstash, Elasticsearch, and Grafana, which you see over there in that diagram on the right side. And so that was kind of what we used as our foundation. We also liked a lot of the high-level use cases. So, back to some of those stories that Ed was talking about, for being able to leverage things like the science registry, which also came out of NetSAGE, which associates like IP addresses with projects and science disciplines. So then you can do, cool visualizations of what science is happening on the network and things like that. So we wanted all that functionality, But we had a few additional kind of more engineering focused and operational focused use cases that were outside of the scope of the original NetSAGE project. So this required us to pull in things like BGP data. There's cases we wanted to look at full IP addresses. Where in NetSAGE, we were building this public dashboard, right, where we were dropping the last octet because we had to worry about things like international privacy law and stuff like that. But this was kind of more, we had use cases where we, for our own private purposes, and we wanted to be able to see those types of things. And also we wanted to add a few additional data sources, and I'll show some of that in a moment, like for example, optical data, or we have a project called High Touch, which is looking at using hardware essentially to look at packets and various data that it can pull out of that. And I think what we came up with is a really kind of cool example of kind of when I think NetSAGE was originally designed, what we could hoped we could do with it, right, in terms of it being really flexible and being able to swap components in and add steps and turn steps off. And I think a precursor to some of the work that Doug talked about last week, if you saw us talk, in terms of the NetSAGE project extending to other areas like campuses and things like that. So I'm not going to get too much into the detail of the various moving parts because Sowmya is going to talk about that, how to deploy it. So right now, I actually just kind of want to jump right into showing you kind of what it does, because I think that's really the best way to get a feel for it. So I'm going to switch over here. I'm going to refresh this. We're working with the latest data here. So this page that I have up right now is our internal dashboard. So unfortunately, it's not public. You have to have an ESnet login to get to it. But what it is this is flow data that it's showing. And this is a system that our engineers or others at ESnet can use to kind of look at the various metrics that we collect. So this is kind of like the launching page, which is just an overview of the entire system. So this is solely based on flow data, what I'm showing here. And so you'll see this pattern a lot. On this one, we have the traffic, the packet rate, and the flow rate. This is for the entire network. We're not doing any deduplication or anything like that. It really, like I said, kind of gives you an idea of what's going on in the system. And then we have kind of various breakdowns that, again, are kind of act as a launching point on devices and sites. And we have a bunch of tabs down here with even more breakdowns. And again, this will be a common theme as I go kind of through some of these dashboards. So for example, if you want to break down of what are the top applications going across the ESnet right now, we have some metadata related to that. There's a table right here. It breaks it down, including the port number, and one down below that actually takes out the individual port number, which you'll see things like grid FTP kind of move up the rankings because it uses a whole bunch of different ports. And so you can kind of see, kind of as you'd expect, XRD is a big application using the LAC that's kind of dominating things right now, which is some grid FTP, some iPerf3, kind of usual suspects, I think, for our community. You'll also see the big unknown here at the top. Again, last week at the NetSAGE talk, there was a good conversation about metadata. This just kind of relates to that. This is kind of an area where we're constantly trying to improve and get more metadata so we can identify traffic like this. And that takes a lot of different forms. So applications and their ports and what they're actually, kind of doing is one of those. So that's a really simple example. It's probably also worth noting we do quite a few roll-ups and things like that. So you can go pretty far back in time. So if I want to switch to the last 6 months of traffic on ESnet, I just can kind of do that. We'll see a few weeks ago, actually, things bumped up quite a bit. I think that's a combination of the LAC data challenge. There's a couple other projects I know that have kind of ramped up some traffic there, which has contributed to some of that. But kind of getting back to more of the engineering use cases, and I'll zoom back into the last day. Let's say you're an engineer and maybe you just brought up a new router, which is something that's happening a lot right now at ESnet as we bring up ESnet 6, and you're curious what's going on with that router. So I'll just pick Chick CR55 here at the top. It's one of our routers in Chicago. You can click on that, get this message because I'm an admin and I touch lots of things, so I thought I wanted to save them, but I don't. So then, you get to this page, which has that same set of graphs you saw at the top, but now it's filtered down just for the router that I selected in Chicago. You get some breakdowns then of the various interfaces on that router. And this is still all flow traffic or flow statistics, no SNMP or anything yet here, just from the flow. So what interfaces and what they're doing. Got information about the interface pairs, who's forwarding to who. and then our breakdowns that we had on the other page. So for this example, let's say I want to drill down into one of these interfaces. This Starlight interface here is not always pick the top one. Let's go number 2. We'll click on that, and we'll see again a variation of those graphs that we often see with the traffic. Quite a bit of stuff is moving across it. So now I think a natural question would be, okay, what is actually going, or what is actually driving the traffic that goes across this interface? So for that, we can use some of these breakdowns. And so I'm going to select the ASs here, which will kind of tell us which ASs and organizations essentially are creating traffic that is going across this interface. So we'll see on the source side, Chicago's one of the big contributor right now, the University of Chicago. IU Research is a big destination right now. That's all well and good. So stuff like source and destination AS, that comes directly from the flow records. But as I mentioned, we had some additional use cases for peering analysis and things like that, where we're able to use some BGP data to get some other views of things. So what we use is to actually collect stuff. So if that picture I had up when the slides were up at the bottom there to kind of collect the stats is something called PM account. It's an open source tool. It's not something we developed, that not only can collect flow data, it can actually collect a bunch of different metrics, but it can actually collect BGP data. And so when a flow record comes in, it can say, okay, what router sent me this flow record, associate that with the correct BGP table, and then take the destination IP address in that flow record and do a lookup to figure out things like the AS path and med value. So that means as I scroll down here, I can also look at things like, okay, for stuff that leaves ESnet, what are the top AS hops? So we'll see Indiana Gigapop is a big one. And what are the actual top AS paths? So we'll see Indiana Gigapop's the top one, but it actually shows up in a few different AS paths. So one actually goes to Hurricane Electric first, then over to Indiana Gigapop before landing in IU Research. Another one that directly goes to Indiana Gigapop and Purdue, similar for IU Research and stuff like that. So it's kind of cool. We can kind of get a view beyond just what's the endpoints, but actually what's happening in between in some cases when stuff leaves our network. And so if I want to drill down into what each AS is doing, so I'm going to click on Indiana Gigapop here. I can get a pretty good view of what traffic on the network is related to Indiana Gigapop. And so we have a graph up here that kind of breaks things down. This one's deduplicated, unlike the first one I showed. So you basically get some breakdowns here again, source and dest. And again, we can look at the AS paths. So when Indiana Gigapop forwards stuff to us, what's the AS path when it leaves the network? So you see some stuff going directly to the University of Chicago, some stuff going across GPN in Nebraska. Likewise, when we get traffic and forward it to something that hits Indiana Gigapop, no matter where it is in the AS path, like basically show us all those paths where it's included. We have a nice table of that down here, and kind of can see all that information, right? So it's kind of cool, again, getting a view of beyond just what's happening on the endpoints, but some of what's happening in between. So these are kind of some of our engineering use cases. As I mentioned, we still wanted a lot of the high level use cases. So for example, we have the science registry, which allows us to see like what type of science is happening on the network. And so for example, in this one, there's a bunch of high energy physics. If we want to see what all the high energy physics traffic is that's going on the network, I can click on this and get a page very similar to the type of thing you can get when you look at the various instantiations of NetSAGE that are out there. And in particular, what I wanted to highlight was the Sankey diagram down here. Now I can't remember if Doug showed this last week, but this was a visualization developed as part of NetSAGE. It's actually in final approval right now with Grafana. It should hopefully become a official plugin any day now. We've submitted it, and we've had to change a couple fonts and things like that, but they seem pretty happy with it. So hopefully that will be pretty soon. Anybody can just install this like any other Grafana plugin and use that. But anyways, it's really great for high level views like this. We can see this kind of source organization, the science discipline here in the middle, and then like the destination organization. But what's cool about this, and kind of demonstrate the flexibility, we can also apply this to lower level applications as well. So everything I've shown so far is flow data. So we've actually also started ingesting SNMP data. And I see a question in the chat that says Sankey, S-A-N-K-E-Y is how you spell that. And there's some variation of that is going to be the name of the Grafana plugin once it's done. So but anyways, so we're ingesting SNMP data as well. And so eventually this will replace, if you're familiar with our current SNMP service called NetBeam, eventually Stardust will replace that. We're hoping actually by the end of the year to have most of the things moved over to that. We're actually collecting all the data. It's just usual migration things, getting applications moved over and stuff like that. So I'm going to switch over to one of our SNMP dashboards, and these are still very much under development. And rather than kind of show you guys the standard utilization graphs and things like that, I'm sure we've all seen those with SNMP data. I kind of wanted to show you an interesting application in the Sankey. So there's some tables here. Again, this is showing just a bunch of stats about a particular router, the Chicago CR55 again. So there's a breakdown of a bunch of ports and stuff like that. But one interesting thing we're able to do, so this router in particular is one of our Nokia routers. And I'm not sure how many of you have actually had to work with the Nokias before, but they have a very interesting way of logically constructing things. It's not, at least in my simplistic view of as a software engineer of the network, it's not nice interfaces and sub interfaces with VLANs and stuff like that. They have these things called service access points, SAPs, which are these constructs that apply policy, and then you can put layer three interfaces and VPNs on top of that. So one cool thing is we collect enough metadata that we can actually create a Sankey that maps how traffic flows through these various constructs from like the physical port to like the layer 3 virtual port. So right here is the Sankey that we put together where the physical port is all the way over on the left. The SAP, which has this weird name right here, is in the middle. And then on the right side, we actually have like the layer 3 virtual interface that you'll see. And the width of the line is based on the volume of traffic that's forwarded to each of these kind of layer 3 ports. So you can see here this top physical port 11C91 has two layer 3 interfaces, a V4 and a V6 one that goes to Fermi. They're actually about even, which is always nice to see. Well, V6 is a little bit behind now. They're more even earlier. So you can kind of see that breakdown. If you scroll down a little bit more, you'll see even bigger splits in some of our other interfaces. So there's actually a lag here. I'll get back to lags in a second, which is a link aggregation group. But anyways, it looks like a single port. And you'll see that's actually split out into a number of different kind of virtual layer 3 ports that go to University of Chicago, University of Wisconsin, Indiana Gigapop, and some LHC1 stuff and things like that. So you can kind of dynamically generate what's going on internally in the router, which is kind of cool. This is just actually a variation of above where the lines are just made to be equal. So if all you care about is really the structure of what's going on with the router, you can see that right away. So just kind of one last thing I wanted to show on this page. I mentioned lags earlier. So those are not a Nokia concept. So probably a lot of us have familiarity with those. We actually have enough metadata we can dynamically generate. This is called a slope graph, another plugin we've submitted to Grafana and will hopefully be accepted soon. It's very much like a Sankey, except it's 2-dimensional and the lines don't vary in size. So right here, we actually have a mapping of the physical ports to a lag. We could build a Sankey that does the same thing. But like I said, we're kind of just playing around with this and kind of show some of the flexibility and things you can do. So those are a couple low-level kind of SNMP things that we're playing around with. Just one last thing I want to show you is on the optical front. So I showed flow data, I showed SNMP data. Now I just want to show you guys real quick. Let me go here to my folders. Some of the optical data we're collecting. So for this, we're using RESTconf, and it's just an interface that some of our transponders have. And we're using metric beat, which is an elastic thing, just it has an HTTP plugin. We're really not doing anything special, just grabbing the JSON from the transponders, shipping it up to Kafka and Logstash and Elasticsearch, just like we do with Flow and SNMP, and processing it just the same way, but then kind of collecting some more of these optical type stats. So the page I'm showing right now is just a quick overview of what's going on the network with the transponders. I always find out optical data a little bit more boring than other data, lots of flat graphs, lots of zeros and things like that. So this is attempting to find interesting things. So this top table right here is looking at something called Q factor, which 12, I guess, means good, and below 12 is bad. And I'm also not an optical expert, so if you have me try to get me to explain any of these stats, I failed miserably. So, but anyways, this has got some of like the lower ones, and so that's kind of a good launching point again for debugging things. To kind of stick with my Midwest bias here and looking at Chicago stuff, I'm going to click the Chicago transponder. And you can kind of drill down into the interface. We have a bunch of stats collected here. Basically error correction stats, chromatic dispersion, optical frequency, optical power. Makes lots of pretty graphs when you look at it. But just kind of the theme of metadata. One other piece we have is all of these transponder connections are part of circuits. And so we have like this hierarchy of circuits that we track in one of our internal databases, and we suck that in as metadata as we ingest this. And so the circuits can consist of transponder port to transponder port connections. And then like higher up in the hierarchy, you can have basically chains of those transponder connections, which ultimately connect, router ports and things like that. So we have all these circuit IDs here. They don't mean a ton probably to you guys or necessarily to me, but they mean stuff to our network engineers. I know this one that starts with B is kind of one of the higher level ones. So if you click on that, you can actually get a view of the circuit. And so you'll see this is that Chicago interface I was looking at is actually part of a circuit that goes from ANL to Starlight. So basically everything's up right now, but if one of these was down, you could kind of quickly see which one was down if the circuit was giving you trouble. There's some stats kind of broken down too, again by interface. So if you want to just kind of look at the circuit and see what's going on, you can do that. And so I'm gonna stop there and go back to the slides. So I think I've kind of quickly gave you an overview of a lot of the different stuff we can do. We're still kind of working on adding more, but obviously there's a lot that kind of goes in underneath the hood to make all this happen. So I'm going to hand it over to Sowmya to kind of talk about all of that.
Thanks, Andy. So I thought we could start this discussion on the technical details by going over the current scale of operations for Stardust. So today, Stardust actually processes about 10,000 events per second on an average, and peaks reach somewhere close to 20,000 events. And originally, Stardust was actually designed with a target of on an average processing 7,000 events and peaks close to like 11,000, 12,000. So you can see that we have actually, in fact, grown even in like the last few months. And from a data retention perspective, so this is more specific to flow data. So the raw data we keep around for 30 days, and we create different aggregates, and we have different policies on those. And we have a replication factor of 1. And currently, we have provisioned for about 147 terabytes of storage. And the plan is we would increase this cluster furthermore as we add more data sources. And I'm pretty sure you're familiar with the diagram on the right. And while there are so many components in the Stardust, the key component to this is the Elasticsearch, the time series database. So I thought we could go a little bit more look at it a little bit more closely. So can you move to the next slide, Andy? So if you take our database cluster itself, it consists of a combination of Elastic and Kibana instances. Currently, we actually have 3 different clusters. So one is the data cluster, which is what you've seen in the Stardust architecture. And that's where we store all our network telemetry data. And that's our biggest cluster. So it has about 23 nodes, 3 dedicated masters, 20 data nodes, and we use hot-warm topology. And so that all the data ingest happens on the hot nodes. So we have 7 of those currently. And after a couple of days, the data gets moved over to the warm nodes and we have 13 warm nodes in the data cluster. Apart from that, we also have a management cluster because we actually monitor pretty much every component in the Stardust, and all that data gets collected in our management cluster. It's slightly smaller in size, about 5 nodes, 3 dedicated masters and 2 data nodes. And finally, we have a small dev cluster as well. And one thing we have maintained is across these 3 clusters, we have ensured that each of these nodes have the same config. Our master node is the smallest with 4 CPUs, 16 gig, and we use AMD processors because when we did this performance testing in Google Cloud, we ran into an issue with like our Intel processors there with hyperthreading. So that's AMD processors don't have that issue, so we've chosen that here. And our hot nodes are 16 CPUs and 64 gig, and we use local SSDs because that was, in terms of performance as well as cost, that's the most efficient. And for warm nodes, we have 8 CPUs and 64 gig, and we actually have 9 terabytes of local SSDs. That's the max Google Cloud allows for each instance. As you can see, the Elastic cluster itself, across these 3, we have about 31 nodes. Apart from that, we have Logstash, Grafana, and so many different clusters. And so managing them manually would become a tedious task. So what we have done is we have actually invested pretty heavily in orchestration. Next slide, Andy. Can we move to the next slide? So what we have done is we actually use Ansible playbooks, and we have created playbooks for pretty much all our different workflows, like creating resources in Google Cloud, be it setting up Kubernetes clusters, deploying services, managing, and all that. And while the database cluster itself runs directly in VMs, we have some of these other components like Logstash, Grafana, as well as Kafka running in Kubernetes clusters. And over there, if you have, when you manage these Kubernetes applications, it can become a bit tedious. And that's where the Kubernetes operators become pretty useful. So these Kubernetes operators, they have these custom resource definitions. So basically what we can do is we can define what we need from an application perspective, and that automatically translates into the different Kubernetes resources that need to get provisioned, like the various pods, stateful sets, deployment sets, or services, load balancers. All those things are automatically provisioned by the operator. And in our case, we actually heavily use that for Kafka. We also use a Postgres operator and a few other things. Next slide, please. So the next thing I wanted to touch upon from an operational perspective is monitoring and alerting. It is very critical, especially when you have a pretty complex system like Stardust. And next slide, Andy. So pretty much every component in Stardust is actually monitored. We use beats. So we use metric beat for collecting system level stats, application statistics, and we use heartbeat for monitoring our service endpoints, file beat for collecting logs, and all this gets stored in the Elasticsearch management cluster that I talked about earlier. And we have built visualizations in Grafana and Kibana based on that. And we also have alerting integrated. So we use ElastAlert. It's a rule-based system, and you can configure various checks. And once a rule is matched, then an alert is triggered, and you have few different options there. We have tested ServiceNow and Slack alerts, but there are quite a few that ElastAlert supports. And another thing I wanted to highlight here is this whole monitoring and alerting infrastructure is basically built based on the same tech stack that we use for our main Stardust platform. So managing the monitoring environment also is pretty easy because it's pretty much the same set of things we are using. Next slide, Andy. So here are some examples of the kind of visualizations we have built for our internal Stardust monitoring. It's pretty, as you can see, it's pretty similar to some of the other graphs that Andy was talking about, which here has been built for the network telemetry. Similarly, we have similar telemetry for our entire Stardust system. And next slide. And not just that, we also look at our overall Stardust application performance. So we look at query latencies, and if there are any, if we notice any performance bottlenecks, this helps us to dig deeper and figure out where the issue is and troubleshoot it. Next slide, Andy. And not just that, we also monitor our own monitoring platform as well. And so we use a combination of Google Cloud monitoring, as well as we've built dashboards to analyze whether these Elast alert rules have triggered, or were there any matches and all that kind of details. And on the top right corner, I've shown a sample alert that gets triggered. So basically, as you can see, there is details about the actual, which component is actually creating that alert, and we have some basic information like when it was triggered, and we also put in the dashboard link, so the engineers, when they actually get this alert, they can actually start quickly troubleshooting the issue. Next slide. And so the other thing I wanted to kind of quickly touch upon, which is critical and has helped us, especially when there are sudden spikes that we notice, or whether it be, in general, like a slow increase in our ingest rate, is scaling and growing the Stardust cluster. So I thought I could just talk about a specific use case and build this scaling part, like how we are addressing the scaling in Stardust based on that. So recently there was actually an aggressive port scanning, which led to an increase in flow data. And as a result, what it meant for Stardust was our ingest rates started spiking up. And when I say increase, basically it actually just doubled. So on an average, I said Stardust processes about 10,000 events per second. That shot up to close to 20,000, and we were seeing even peaks of like 25,000 events per second. And so how did we first encounter this issue? Alerts were triggered for Kafka, and and the dashboards basically quickly helped us to analyze and figure out that it was actually an ingest issue. And so what we did initially was to add more Logstash nodes so that the pipeline could keep up with the ingest rate. And as we increased the Logstash nodes, now what we realized was our storage capacity was starting to hit the thresholds. And so next we started increasing our storage. And while all this was happening, our engineers were further debugging the issue, and eventually it was figured out that it was just caused by a lot of single packet flows. And so what we eventually ended up doing was modify our ingest pipeline to filter the packets. While all this was going on, the thing to highlight is that Stardust was actually fully functioning and accessible to our users during the whole time. And this was possible because we were able to scale quickly. We were able to know when to scale, how to scale, because we have this alerting and monitoring. And at the same time, we were able to scale because the Stardust architecture is loosely coupled. So we were able to scale only those components that need to be scaled. Like, for example, if the ingest rate was spiking, we were scaling just the Logstash nodes. Or if Kafka is the bottleneck, then we are able to just increase the capacity for Kafka and all that. And similarly, the third thing that helps is, especially when everybody's working under time pressure, doing these things manually would be more error prone and less efficient. So now, since we have this automated orchestration, that actually helped us to quickly roll out changes and all that. Next slide. And so what are some of the lessons learned from this, and which basically we are taking it and incorporating it into our Stardust architecture? Is one thing we've realized is Stardust already has separate pipelines for different data sources, but having multiple queues even within those data sources is actually useful. Like, for example, if we have a separate flow for separate pipeline for the single packet flows, then we can deal with that set of data separately. We can apply a different set of policies on that. And the second thing we realized was slow is not always bad. So even though it looked like Logstash was our weakest link, it is actually, in fact, helping us to, it was helping us to protect our storage from completely crashing down. Next slide, Andy. And the third thing we learned through this experience was we need to plan ahead for storage cluster changes, especially for a cluster of the size that we have currently. When we apply changes like adding a node or rebalancing the shards, or maybe changing some shard or index settings, all those take some time to propagate, and eventually it takes a while for the cluster to reach a steady state. So these are things that we need to push well ahead of time and not just wait until the last minute. And apart from that, the other 2 points I've already highlighted: monitoring, alerting is critical, as well as automation helps, especially if you want to keep rolling these out like pretty quickly, or just maintain such a wide set of components. And so that's actually a very brief overview of how we are managing and operating Stardust on an everyday basis. And now I hand it back to Ed.
Yeah, thanks, Sowmya. And so what I wanted to do now is talk a little bit about we've sort of highlighted how we have addressed the sort of the engineering and network operation use cases related to some of this data we collect. What I want to do is pivot a little bit, move up the stack a little bit, talk about I guess community engagement and value proposition. So what I will do is in particular talk about, I'm going to show you a little bit of some demos here, so bear with me.
You're welcome to take over now, Ed.
Awesome. All righty. Let's see here. All right. Does that display okay for everybody? So this is, this is a, we call this the engage map. This is something we're doing internally with the science engagement team. This is probably familiar to a lot of people. Oftentimes executives want these executive dashboards or single panes of glass, that sort of thing, where you might have some key demographic, bulk, baseball card like summaries at the top, might have a map, might have some vital stats down below, right? And so we of course have to do that for some of our constituents at ESnet as well. One of the things I wanted to highlight, Jen mentioned on the Slack channel that Katrina joined ESnet, and she has, and we've been keeping her busy. It's been great having some folks with some biz background on the team. We've recently been looking at how to get a geographic visualization that can not only show sort of let's say SNMP data and overall traffic use, but one of the things we're trying to do is use these visuals to show things like, in this case, we're not just showing the overall usage, we're showing the flow data and hop by hop what amount of data on each link is sourced or sunk by NERSC in this case. And so that's a pretty powerful thing for us, because we can do it based on any of the metadata we have, right? So whether we want to show here's all the traffic going to NERSC, or whether we want to show all the iPerf3 traffic or all the XRootD, we can tune the map to a specific constituent, whether it be sort of a science project using a certain set of protocols, or you name it, right? So this is a very similar to what Andy was showing, just it's tailored to I'd say a different user base, right? The other thing we've been working on here is this what we call a chord diagram right here. So this is another new thing we've been developing, and we are working with to release that open source as well. It's essentially it's just another way of showing in a sort of radial form the interactions of a source and destination. In this case, we're just showing top talkers at an organizational level. So you can see here that Argonne is sending a truckload of data to NERSC, and then NERSC in turn is sending a bunch of data to JISC and some other folks, right? So it just gives you a quick, real high level view of what's going on, right? The other thing I wanted to show really quick is that Stardust, we've of course been using it for network data, but the other thing we did was figure out to what extent can we use it for other types of data that might not be network measurement based, but maybe more purely metadata almost, right? And so this is an example of taking those same tools and paradigms, and what we did is we imported some DOE user survey data that was gathered back in 2019. So they do this annually. It's sort of a wetware based survey where they ask people to say what facilities are using, and we get counts and aggregate data. It's shared publicly in the form of spreadsheets. And so we took that data, massaged it a little bit by georeferencing it, and then threw it in the Stardust just to see what we could do. And you can see here it's quite useful. We can then we can zoom in and constrain things by different projects or by different countries, that sort of thing, right? So you can do these cross filters. You can see the the map down below may allow you to see what's going on there, right? So these kind of things allow us to then go from network operations and engineering to talking about where our stakeholders are, how they impact the network, and maybe how that changes in the future, right? And so I just want to kind of highlight that. It's one thing. Next thing I wanted to show is some stuff that's not even fully baked, but just stuff we've been tinkering around. And mostly we're just exploring ways of showing data and visualizing it in new ways, right? And so this is an example of some of that same data that came out of that survey. What I wanted to do is figure out if there's a way we could show sort of all of the stakeholders that might be interacting with the Joint Genome Institute, for instance, in this case, and do it in a way that's visually not just a complete spaghetti bowl mess. And so this is using a technique called force edge bundling. Some of this capabilities basically comes with the D3 library, suite of libraries if you've ever used that. And so this just shows sort of a unique way of visualizing sort of global impact of a given science project in terms of sort of the relationships they have with organizations. It's not colored in any way based on network load. It's just purely based on that survey data, but you can get a sense of visually how you might apply this in certain contexts. So that's the one of the visuals we've been working on. The next one does get back to sort of network topologies. And so this is something I've been playing around with because maintaining maps, especially during network upgrades, is tedious and nobody enjoys it, right? And because things change, bit rot occurs, and everybody wishes to have maps that auto update. And so this is one of the things we did to experiment. Again, this is using D3 and a variety of, within D3, it has a variety of, I guess you could call them force simulation capabilities to help you with layout. And so what I wanted to do is just show you really quick. This is a map here. It kind of represents ESnet. It's a little bit dated and it's a little bit simplified. It's router to router topology. It's not true links. But what I wanted to show is what happens with some of these force layout simulators when we play around with some of the parameters, right? So as an example, the gray dots represent just the kind of waypoints along a path. And so what we can do is we can make those a lot longer, and you can see you can make it really kind of angry and the map looks bad, right? But what we can do is tune these things, right? And so, but let's say that the Northeast here is pretty crowded. Are there ways that we can make that a little bit clearer? And so one of the things we were experimenting with was this idea of geographic simplification. So for instance, if we took all of the routers that were in the Chicago area and sort of group them together and call them logically one thing based on a lat long, would that help the visual representation? And so the second dial here allows us to do that. You can see what I'm doing is removing significant digits off of the lat longs, and the topology is starting to simplify. The number of lines is reducing. And I can get that all the way down to, okay, so here's a single point, right? And I can take that to extremes by basically just saying I can even truncate that and round it even beyond into the major, so into the major latitude integer, long integers. But we'll just take it back there. So the other thing we can do though is play around with these forces, right? So you can see there, if I click on this, it's starting to expand out. And I can change some of these parameters and get the map to start to A, have the circuits avoid each other automatically, and B, tune it in a way that makes it look perhaps in some ways a little more visually appealing without having the human have to do it by hand each time, right? And so this technique has promise. I don't know that it'll get us everything we want to do, but it is an interesting technology and has been a sort of a fun exploration. So I just want to show that because it's something that we're looking at as we develop sort of mapping capabilities. There's a lot of folks in the community working on that, including IU. And so we've been trying to collaborate with them and trying to find ways to create good capabilities that we can share with the community, right? I think is what I'd say there. So I'll pause there on the demos because you guys have seen a lot of good stuff. In terms of the future, we basically, I think what we can expect is we're going to continue to refine our technical capabilities. So whether that be new data types, although we have quite a few now, there are a couple of additional ones that we are eyeing. So in particular, we have this ESnet 6 high touch project, which is essentially provides a variety of ways of measuring the network using hardware accelerated deep packet techniques. I won't go into too many details because it's a whole separate talk itself. And then of course, the LHC community is doing a lot of great work with something called Firefly, which allows them, or allows us, if we have that data, to correlate science workflow metadata to network traffic metadata, and allow us to look at network usage not as a sort of behavior of sites, but as a behavior of science, which I think is a really key pivot. And then of course, we've talked about this idea of continuing to innovate visually, and I showed some of that. And obviously having Katrina on board has been a huge boon there. So the second major area, though, is in general is in COVID, unfortunately, I think has really sort of put a damper on some of the enthusiasm. Is we want to continue to contribute in the R&E community, whether that be through the contributions to metadata registries like the NetSAGE Science Registry, or whether it's sharing tools, tactics, and lessons learned like we are today, or possibly even that direct sharing of research with researchers or others of data when it's appropriately shared, right, with protections and stuff like that. So, we see a lot of opportunities for collaboration in the community going forward. And I think lastly for us, it's figuring out how to help scientists move data and remove that friction from their workflows. And so whether that's figuring out how to share data bidirectionally with them, or whether that's creating focused analytics, that's always going to be something that we're keen to help with, given our mission. So I will stop there, and I realize we blew my 40-minute target. That's okay. That's the first time we've done this full-scale talk, so please bear with us. But yeah, so I'll end there and ask if anybody has any questions.
All right. Well, thank you, Ed. And I will ask if anybody does have any additional questions, just put them into the chat. We already answered a couple in there, which I'll just repeat for the sake of the recording. John Graham was asking about the name of the plugin that you were demoing earlier, and that's a Sankey plugin. The flow sampling rate that you guys are executing right now is 1 out of 1,000. I guess a follow-up to that, Ed, is that a configurable thing? I'm assuming that if you go higher on that, of course, data rates will increase astronomically.
Yeah, well, it may or may not, and even if it did, I mean, we didn't really hit on this hard, but one of the properties of the Stardust, and based on Elastic, is it does scale linearly, and there are others in the community like like IAU that are operating Elastic at a much larger scale than us for security analytics, and so we know that we have confidence that we could scale to a much higher level if we need.
Okay. And then you and Jill were going back and forth on NetBeam API versus Stardust API and the similarities and differences there. And Ed is going to brew a celebratory beer, it sounds like, as well.
Yep. Yeah. Although, we'll have to wait until the next time we can actually all get together to consume it. But yeah, sure. I'll give each of you an IOU. Give me about 6 months.
All right, we got 2 last questions here. Do you keep every single flow, or do you discard certain flows, say below a certain size threshold? Yeah,
where we're at right now is we keep all of the flows with the caveat that the what we are doing today is we're keeping this, when we literally earlier this week put this modification in, we are differentially treating single packet flows as things we retain for 7 days. All other flows we keep for 30 unaggregated, and then in addition to that, we maintain a longer time horizon on aggregated data.
Okay. And then last one, since we're at the top of the hour here, would this be suitable for other networks to adopt wholesale, or would you recommend we reuse portions but tweak it to our needs?
I mean, the design pattern is something I think that any network could benefit from. Some of the displays sort of stuff will always, of course, need to be tweaked to your needs. Metadata, the same thing. A lot of the metadata comes out of ESDB or other sources, but the building blocks, we think that where the real strength there is that there are general purpose building blocks that could be adapted. And I think that when we think about collaboration in the community, talking about how to use those building blocks effectively, there's a lot of lessons learned there that we'd love to share and would encourage folks to contemplate.
Okay, and then I lied. There is one more. How much of this data will be made accessible to the public in the future?
Yeah, so that's something that, that of course with flow data, that there's some sensitivities around that, and that's something we're still sort of trying to figure out. A lot of that is internal use case. The SNMP data we already share, and PerfSONAR data we already share. So that's something that we'll refine going forward. One of the really great things about the building block in particular of Elasticsearch is we do have the means to do sort of row level metadata based access control of what we share. So there are some technical, whatever our policies we end up with, and what data we can share, we have a technical means to control that and share it sort of safely, as it were.
All right. Well, that was it for the questions. So thank you, Ed, Sowmya, and Andy. Great stuff. We'll make sure that this gets posted. And for those that are still on, the talk next week is going to be another ESnet talk from Charles Shiflett, and he is going to be talking about a new tool that ESnet's been playing with called ESCP, which, if you look at that name, it is a play on SCP, the well-known SSH-based file transfer tool. And we're going to be talking about how that's we've developed this and tried to get it to be used in high-speed data transfer environments. So more details will be sent on that later in the week. So hope everybody has a good weekend, and we'll talk to you all soon.
Thanks all.